It is commonly noted that sunrises look different, perhaps bluer, than sunsets. Is there actually such a difference? And if yes, what can be the cause behind it? Sunlight contains all wavelengths of visible light in a proportion so that together they appear more or less white. However, tiny particles in the atmosphere scatter this visible light according to what is called Rayleigh scattering, so short wavelengths are scattered more than long wavelengths. And this is responsible for the blue color of the sky. And the way it works is that sunlight has to pass through a certain distance within the atmosphere, and proportionally to that, a certain amount of the short wavelength light is scattered away. That's why the sky is blue, and the remaining direct sunlight still appears more or less white. However, when the sun is near the horizon, the sunlight has to travel through a longer distance in the atmosphere, so more of the blue light is scattered away, and that's what gives sunrises and sunsets their red appearance. Larger molecules in the atmosphere and larger particles, however, scatter light according to what is called Mie Scatter, where all frequencies are scattered equally, and this is why in white sunlight, for example, clouds appear white. So the question is whether the size of these two major mechanisms and their effects can systematically differ in the morning versus in the evening. And when it comes to Rayleigh scatter, air pressure actually does affect it, and thus also the movement of weather systems. And this is the reason behind the ancient observation and weather forecast like red sky in the morning, shepherds take warning. But these effects are always local and temporary, and so they do not account for any systematic difference across the globe and across time, so on average between mornings and evenings and the color of sunrises versus sunsets. This is not the case with Mie Scatter, however, where there is a systematic difference. In the morning the air is cleaner, and this gives a sharper, tidier appearance on average to sunrises, while in sunsets, especially in highly polluted places, more Mie Scatter means a more blurry and oftentimes even washed out appearance to the sunset. However, with Mie Scatter, we've seen that this affects all wavelengths equally, and therefore it doesn't really change the overall color temperature of the phenomenon. And then there's a third physical mechanism which could play a role here, and that is the Doppler effect. So the surface of the Earth moves towards the sun at sunrise, and this shifts the light towards shorter wavelengths, so bluer light. But at the velocity of the surface of the Earth, this phenomenon is absolutely minuscule and can be neglected here. So none of these three major mechanisms can really account for any systematic, perceivable, significant difference between the color temperature of sunrises as opposed to that of sunsets. However, there is one factor which can, and that is also much more interesting to me and to my profession, and that is you, the viewer. So basically, color is not a property of light, but it's a property of the percept and perception. So any wavelength of light can be perceived as virtually any color, depending on the situation and the viewer. And this is illustrated well by all kinds of color illusions. This is an example here. If you stare at the cross in the center, every time one of these purple discs disappears, The light that reaches your eye afterwards is the same white light that is the background of the image. However, what you're going to see is a disk of the complementary color to this purple, so something between blue and green, and this is an adaptation after effect. Similarly here, if you look at this point for a while, after some time, the green underneath the rotating red structure is going to seem brighter and more saturated than the outer rim of the same green disk. Again, this is an adaptation effect, which takes place already after a few seconds. But the visual system has various mechanisms of adaptation, some of which also take place across a longer time duration. So, when you have spent your whole night in darkness, ideally, your perceptual system is going to be adapted to it, and afterwards, the very same red light of the sun near the horizon is going to seem brighter and bluer, as opposed to when you have spent your whole day outdoors in bright blue daylight. The same light from the setting sun is going to seem redder and dimmer, and this is a significant effect, and it's most likely the major reason why people have observed a difference in color between sunrises and sunsets. Now, it's worth to note here that this is not to be confused with the common current practice and trend towards intentionally exposing ourselves to blue-rich, bright electric light early in the morning with the intention to help us wake up. And this is a trick that works actually, regardless whether you use powerful LEDs in your regular luminaires or purposefully built setups for this reason. But it works more or less similarly to coffee, so there seems to be a trade-off between general alertness and performance in specific tasks, and also it is very unnatural, so it's not balanced. The blue light is not balanced with other frequencies of visible light and invisible light as well, and also the temporal dynamics are unnatural. So in daylight, the blue content and the overall intensity of light as well as blue light keeps rising throughout the morning gradually, and it only reaches its peak at solar noon. So this type of practice with electric light is it works, but it's a trade-off, and it holds some potential dangers as well, about which I'm going to talk more in later videos.